Now we can conceptualize the difference between the electric potential energy and the electric potential, because they're different, although they are very, very related. Okay, so to create an electric field, we have a nice uniform electric field created by a parallel plate capacitor. We said this is point number 1, this is point number 2. If a positive test charge is placed at this point, then the charge will move under the influence of energy difference from point 1 to point 2. If it's moving from point 1 to point 2, then you should know that the electric potential energy at 1 must be bigger than the electric potential energy at 2. And this movement is coming under the work done from point 1 to 2, and the work done from point 1 to 2 is the electric potential energy 1 minus the electric potential energy at 2. Okay, now let's define the electric potential. So the electric potential is simply defined as the work done from point 1 to 2 on the positive test charge. So that is the difference between the electric potential energy and the electric potential. The electric potential energy is an energy. That's why we call it work. Now the electric potential is the work done from point 1 to 2 on the positive charge, or transferring the positive charge from point 1 to point 2. So it's work done on the charge. That's called the electric potential. Okay, now let's define electric potential. The electric potential for a point, I'm going to call it, for example, V1 here, is equal to E P E1 divided by Q0. Because we're talking about electric potential, and that's electric potential in general. Now we can define so I'm going to call this point here, it has V1, and here this point has electric potential V2. So V2 is the same as EPE2 divided by Q0. So we define something called the electric potential. Now here's the thing. There is no such a thing in physics called electric potential. It actually does not exist, but we are defining it. And the reason the electric potential does not exist is that you're always trying to compare 2 points together. So point 1 and point 2. And when you try to calculate the electric potential, you don't do that. You actually calculate the electric potential difference between these 2 points. So here, you do not calculate V on its own, so that does not exist. You do not calculate V2 on this own, it does not exist. It does not, because you always have to compare the electric potential to a reference point. Just like when we talk about like lifting up the ball, right, above the ground with a height h. You're going to say, okay, what is the potential of this ball to do work? Well, if you actually take h all the way up, so like you're lifting the ground up and you put the ball on the ground, then the potential for this ball is 0. You always have to compare with another point. So that's why we compare with this point to this point. So now we use this as a reference. Okay? The same thing applies for the electric field. You always have to have a difference. All right? For example, you're getting 120 volts in the wall inside your house. Okay? So 120 volts actually is not the correct way to describe it. You're not getting 120 volts. You are getting 120 volts compared to another line that is probably called the neutral line, and this neutral line is at 0 volts. So you are comparing the 120 volts to the 0 point, and that's why we call it 120 volts. or 120 volts to the ground, and the ground is 0, and that's why we call it 120 volts. People just don't repeat that. They don't say, well, I get 120 volts compared to the neutral line or to the ground line. They don't do that because it becomes redundant. But actually, every time you measure the voltage, you are not actually measuring the voltage itself. You are measuring the voltage compared to another point. And that's why when you get 120 volts at home, you are comparing it to the ground. For example, that's the ground, the universal sign for a ground. It was found, too, that the difference in the electric potential, which is V2 minus V1, that's the difference, is equal to minus W12 over Q0. I'm getting this here from here, so that's the same thing, but because it starts with the V2, but W starts with 1, delta V starts with 0.2, and W starts with 0.1, so they're opposite to each other. So now I can write from both all of this that delta V is equal to minus W2 over Q0, so I can write it down as EP. Delta V is equal to EPE2 divided by Q0 minus EPE1 divided by Q0. So that's the change in delta V as you can see it. And this quantity is equal to minus W1 2 over Q0. Thank you. That's good for now.